Hello. In this video we will discuss what torque is and how to calculate it. We have mentioned torque before in the context of this equation. This equation says that the angular acceleration of an object equals the torque exerted on that object, divided by its rotational inertia. From this equation we can think about torque as the thing that causes angular acceleration. This is very similar to how force is the thing that causes a linear acceleration. Therefore we can think of torque as the rotational equivalent of force. So where does torque come from? Well, imagine we have an object that is free to rotate about this axis. We draw this line here that connects the object to the axis, which I will call R. Now imagine that there is some force that acts on the object. One component of the force is parallel to the R line, so that force tries to accelerate the object in the radial direction, which does not cause a rotation. A rotation is only along the tangential direction. The other component of the force, though, does cause a tangential acceleration, which means it also causes an angular acceleration. We can write this equation, which says that the perpendicular force equals the mass times the tangential acceleration. Now we are going to try to turn this equation here into this equation here. In so doing, we will find out what torque actually is, since if we can get one side of our equation to equal I times alpha, then the other side equals the torque. The first step is to remember that the angular acceleration times the r equals the tangential acceleration. So let's sub that in. Next, let's recall that I equals the mass times r squared. So let's solve this for mass so that we can sub it into the mass in our equation. We get I divided by r squared, and we just put that into our equation. Now r divided by r squared is just going to be 1 over r. Now let's move that r over to the other side. Great! Now we have I times alpha on one side, so the other side must be the torque. Therefore we can say the torque equals the perpendicular force times the length of r. Now if we know what the angle is between r and the force, then we can find what this perpendicular force is in terms of the force magnitude and the angle. It's a straightforward trigonometry exercise. Go ahead, give it a shot. Alright, the answer is that F perp equals the force times the sine of the angle. Therefore, we can write the torque as this formula. So now, let's assign some numbers here and calculate the torque exerted in this problem. We plug in our numbers with their units. Sine of 30 degrees equals a half, by the way. So if we multiply everything together, we'll get 15 Newton meters. That is the value of the torque. You should know that, even though Newton times meter happens to be the same unit as energy and work, torque is a very different quantity than energy, so don't call this a joule. Now, what is the angular acceleration? Well, angular acceleration is the torque divided by the rotational inertia. So let's first compute the rotational inertia. I equals the mass times r squared, so we have 1 kilogram times 3 meters squared, so we get 9 kilogram meters squared. So the angular acceleration is 15 Newton meters of torque divided by 9 kilogram meters squared of rotational inertia. The units of a Newton are actually a kilogram meter per second squared, so we can write this equation. Many of the units cancel, and our answer is 1.67 per second squared. That is our angular acceleration. If you are wondering where the unit of degrees is, that's a good point, and you should realize that the angular acceleration in this formula is measured in radians, which doesn't have a dimension like degrees. Let's take a look at another example. Imagine we have a seesaw, but one side of the seesaw is twice as long as the other. On one end sits a kid who has a mass of big M. What size mass would you need to place on the other end in order to balance the child? Balancing means that, assuming the seesaw is sitting still, how can you ensure that it continues to do so? So what we are really asking is, how can we make the angular acceleration 0? To solve this problem, let's place a mass of little m on this side, and our goal will be to find what that mass needs to be in order that angular acceleration be 0. Let's write out this equation. The sum of torques equals I times alpha. For our problem, we can set alpha equal to 0, since that is the condition we are solving for. So now we need to sum up the torques. Well, what are the torques? First, we should probably figure out what the forces are. Each mass feels a force of gravity, pulling it straight down. Now, it's true that there is also some kind of normal force pushing back up on the masses from the seesaw, and there's a normal force that the seesaw feels from the masses. However, we are not going to worry about that right now. After all, we are treating the entire seesaw plus masses as a single rotating object, so any forces acting between the seesaw and the masses are internal forces, which cancel when we consider the system as a whole. This is because those normal forces are equal and opposite, and since we consider this whole thing as a single object, those equal and opposite forces will cancel out. So let's translate these forces into torques, starting with the force on the left. The gravity is acting perpendicular to the line that connects the axis to the force. Therefore, the perpendicular component of the force is simply little m times g, and the length of the line is 2 times L. Therefore, the torque has a magnitude of 2mg times L. Since it is acting to try to rotate the object in a counterclockwise direction, we will call it positive. Now for the force on the right. That force is also acting perpendicular to the connecting line, but this line only has a length of L. Therefore, the torque has a magnitude of big M times g times L. Because it is trying to rotate the seesaw in a clockwise direction, we will give it a negative sign. So now let's put this into our equation here. And then let's solve for little m, which is what we want to know. So let's move the two terms to opposite sides. Now each term has a g and a L term, so those cancel. Dividing both sides by 2, we get that little m equals half of big M. So it takes a mass of half the size to balance the child. This phenomena of needing minimal force to cause a lot of torque is called leverage, and is used in all sorts of everyday tools, like scissors, pliers, wheelbarrows, and much more. Now, I'd just like to point out that if the seesaw was not flat, and we wanted to know how to balance it and keep it in that position, the problem would be a bit different. Gravity would not be acting perpendicular to the seesaw, and so you would have to know what the angle here is, so that you could use this formula. Let's summarize what we've learned. Torque is a quantity that causes angular acceleration. It is related to the force on an object according to this formula, where r is the distance between the axis and the place where force is applied, and angle is the angle shown in the diagram. The units of torque are Newton times meter, which looks the same as the units of energy, even though torque is not a form of energy. And that's it.